Hello everyone, and welcome to the week 15 review for Math 2414. This is going to be the last review for this semester. And in this one, we will be covering just, some more power series. We'll be going over some more radius and interval of convergence. And we'll talk a bit about converting functions to power series and finding power series representations for other functions. All right, so let's jump right in. We'll do a quick example reviewing some things from last week. So if you'll recall, if we have a power series, and it looks like, let's say the sum from n equals 0 to infinity of x plus 1 to the n divided by 4 to the n, well, we can find the radius of convergence of this series by using the ratio test. So if we apply the ratio test, we're going to want to take the limit as n approaches infinity of the absolute value of x plus 1 to the n plus 1 over 4 to the n plus 1 divided by x plus 1 to the n over 4 to the n. So I'm just going to multiply by the reciprocal, 4 to the n over x plus 1 to the n. And simplifying this, I can simplify my x plus 1 to the n plus 1. That's just an x plus 1. And my 4 to the n and 4 to the n plus 1 simplified is simply a 4. And this limit is, of course, the absolute value of x plus 1 divided by 4. And I know that my ratio test says that my series will converge if this value is less than 1. So I need to have that the absolute value of x plus 1 is smaller than 4. Now, once I get the coefficient on my x term to be just 1, I can read off my radius of convergence right here. So my radius is equal to 4. If I wanted to find my interval, I can drop my absolute value bars by saying negative 4 is smaller than x plus 1 is smaller than 4, and then subtracting 1 from each side gives negative 5 is smaller than x is less than 3. Now, of course, in order to make sure that everything is all fine and dandy, I need to check my endpoints as well. So if I plug in negative 5 for x, then I get sum negative 5 plus 1, which is negative 4, pardon. Negative 4 to the n over 4 to the n, which is just the sum of negative 1 to the n, which of course diverges. So negative 5 is not included in my interval of convergence. And similarly, if I plug in 3, I have 4 to the n over 4 to the n, which is the sum of 1. Now, of course, the limit of 1 isn't 0, so this will diverge as well. So I can write my interval as being negative 5 to negative 3, or to positive 3. Alrighty, so go ahead and try out a couple of practice problems for this. Suppose, first off, go ahead and do the sum from 1 to infinity of x plus 1 to the n divided by n squared for the n. And this one's pretty similar to the last one. And then lastly, we'll do the sum from n equals 1 to infinity, this time of 2x plus 1 to the n divided by 5 to the n root n. And I will give you a few minutes to work through these. All right, let's go over these problems. Again, we're just going to be applying the ratio test. First one, we're going to take the limit as n goes to infinity of a sub n plus 1. So x plus 1 to the n plus 1. This time it's going to be over n plus 1 squared times 4 to the n plus 1. Times, again, the reciprocal, which is going to be n squared 4 to the n over x plus 1 to the n. And this becomes the limit, if I cancel things, as n approaches infinity of x plus 1 times n squared divided by 4 times n plus 1 squared, which is the absolute value of x plus 1 over 4, times the limit as n approaches infinity of the absolute value of n squared over n plus 1 squared. And we can solve this limit in many ways. You could apply L'Hopital's. You could say it's a balanced equation, so I'm just going to look at the coefficients from top and bottom, which is basically dividing everything by n squared. Regardless, the limit comes out to be 1, so we have 1 times x plus 1 over 4 gets us x plus 1 over 4. We know this should be smaller than 1, so we get, again, x plus 1 needs to be smaller than 4, so our radius is 4. Next, we need to check and see if the endpoints converge. So again, we would say that negative 4 is smaller than x plus 1 is smaller than 4, so then negative 5 is smaller than x is smaller than 3. Our first endpoint of negative 5, we would take the sum from n equals 1 to infinity. Negative 5 plus 1 is negative 4. Negative 4 to the n over 4 to the n is negative 1 to the n over n squared. This, of course, converges. You could say it's by p-series test. It'll converge absolutely. Similarly, if we have the sum from 1 to infinity, if we plug in x equals 3, you get 4 to the n over 4 to the n. That cancels, we're left with 1 over n squared, which also converges. Then our interval of convergence is going to be negative 5 to positive 3 inclusive. And again, our radius was 4. For the second one, we're going to do basically the same thing. Apply the ratio test. The limit as n approaches infinity of 2x plus 1 to the n plus 1 over 5 to the n plus 1 square root of n plus 1 times the reciprocal, so 5 to the n square root n divided by 2x plus 1 to the n. Again, we're going to simplify and cancel wherever we can. This is the limit as n approaches infinity. We're left with 1, 2x plus 1 on top. The 5 to the n and 5 to the n plus 1 are going to cancel mostly, leaving us with a 5. We also have on top a square root n and on bottom a square root of n plus 1. Again, our 2x plus 1 and our 5 are independent of our limit, so we can write this as 2x plus 1 divided by 5 times the limit as n approaches infinity of square root n over square root of n plus 1. Apologies, this should be an absolute value. And this limit, square root n over square root n plus 1, in this case, we're going to divide everything by square root n. On top, we would get 1. On bottom, we would get essentially inside the square root, we would have 1 plus 1 over n, which, of course, goes to 1 as n goes to infinity. So we have 1 over 1, which is 1. So this limit is the absolute value of 2x plus 1 divided by 5. Now, if we have 2x plus 1 divided by 5, that needs to be smaller than 1. So the absolute value of 2x plus 1 needs to be smaller than 5, multiplying everything by 5. And then continuing onward, we can't actually say that 5 is our radius of convergence because the coefficient on our x is not equal to 1. So in order to make that equal to 1, what we need to do is we need to divide everything by 2. So divide everything by 2, and we get x plus 1/2 is smaller than 5/2. So our radius is equal to 5/2. Next, we can see that negative 5/2 would be smaller than x plus 1/2 would be smaller than 5/2, which means subtracting 1/2 from each side, we get negative 3 is smaller than x is smaller than 2. Now, again, we need to check our endpoints. We plug in x is equal to negative 3. You get negative 6 plus 1 is negative 5. Negative 5 to the n over 5 to the n simplifies to a negative 1 to the n. Now, as far as whether this series converges, well, it's an alternating series. Let's go ahead and apply the alternating series test. Obviously, the limit as n goes to infinity is going to be 0 because we have the square root n on the denominator. The square root n goes to infinity. 1 over infinity is 0. So limit as n approaches infinity of 1 over root n is equal to 0. That's the first thing satisfied. Next, we need to show that the terms, each term is smaller than the one that came before it. So a sub n plus 1 is equal to 1 over root n plus 1. And I'm going to say that this one is smaller than 1 over square root n, which is my a sub n. And if I cross multiply, then I get that square root of n is smaller than square root of n plus 1. If I square both sides, I have n less than n plus 1. So 0 is less than 1, which is of course true. So both of the terms, both conditions for my alternating series test are met, so this one converges. And this was specifically when x is equal to negative 3. If we take x equal to 2, then we have the sum 2x plus 1 would be 5. 5 to the n over 5 to the n is just 1. So we'd have sum n equals 1 to infinity of 1 over square root n. And this one diverges by p series. So it diverges when x is equal to 2. Then overall, our interval is going to be negative 3 to positive 2, where negative 3 is included, but positive 2 is not. And that's our answer. All right. So that was kind of a review of what we did last week. Now let's talk a bit about something a little more exciting. If you'll recall, we could find the sum of a geometric series, r to the n, and we said that this sum was equal to 1 over 1 minus r, provided that, of course, r was smaller than 1. Well then, what if I replaced r with an x? This is a function of x, but I know that this should be equivalent to the sum from n equals 0 to infinity of x to the n, provided, of course, that the magnitude of x is smaller than 1. Well, what I've done here is I've come up with a power series representation of a function. And you might be thinking, well, why is this useful? Well, let's take a look at this. If I wrote out this, I could write this out. First term would be 1, second term would be x, third term x squared, and so on. The neat thing about this is it's a polynomial. And polynomials, it's really easy to do things like take derivatives, take integrals, plug in values. We don't have any of these nasty little division things where reciprocals, stuff like that. And as it turns out, we can actually come up with a power series representation that is a polynomial for a lot of different functions. We can come up with them for exponentials. We can come up with them for trig functions. We can come up with them for pretty much any function that you can think of, provided you can take its derivative. So you're like, okay, all that's great, but you've only shown me a function representation for 1 over 1 minus x. All right. Let's say we have instead x divided by 1 plus x squared. And we wanted to find a power series representation. Well, I am trying to write this as closely as possible to this form, 1 over 1 minus r. So to get a 1 on top, I'm just going to move my x out. And then on bottom, I need a 1 minus r squared. So instead of having 1 over 1 plus x squared, I'm going to have 1 over 1 minus negative x squared. Perfect. I can write this part as a sum from n equals 0 to infinity of negative x squared to the n. That'll give me negative 1 to the n. Then x squared to the n is like x to the 2n. And now I can just multiply my x in there. Just putting in one more x will make that an exponent of 2n plus 1. And there you go. I found a nice power series representation for x divided by 1 plus x squared. Now, go ahead and try it for a few of these. Again, I'm just asking you to find a power series representation. Um, and I'll give you a few minutes All right, let's go over these problems. The first one, if you're particularly clever, you can actually notice that this is 1 over 1 plus x squared plus 2x plus 1, which is 1 over 1 plus x plus 1 squared, which is 1 over 1 minus negative x plus 1 squared. Now we can, of course, use our a over 1 minus r to write this as sum from n equals 0 to infinity of negative x plus 1 squared to the n, which is the sum from n equals 0 to infinity of negative 1 to the n, x plus 1 squared to the n, which is sum from n equals 0 to infinity, negative 1 to the n, x plus 1 to the 2n. And there we go. There's our power series representation. Alrighty. Next up, our second one, I'm going to rewrite this as x squared times 1 over 4 minus x. Of course, I want this to be a 1 minus something. So I'm going to divide everything by 4. X squared times 1/4 over 1 minus x over 4, which is x squared over 4 times 1 over 1 minus x over 4, which is x squared over 4, sum from n equals 0 to infinity of x over 4 to the n. Now, if I take that x squared over 4 times n equals 0 to infinity, x over 4 to the nth, well, I can write that as x squared over 4 sum n equals 0 to infinity, x to the n over 4 to the n. Now, if I multiply my x squared and my 4 inside, well, suddenly I have one more 4. So sum n equals 0 to infinity of 4 to the n plus 1 on the bottom, and on top I've got 2 more x's, so x to the n plus 2. And that'll be my power series representation for the second one. Finally, for the third one, well, I could multiply everything out and make it a 1 minus something. Alternatively, what if I wanted to do partial fractions on this? That's another option. So I have a over x plus 1 plus b over x minus 2, which tells me that I should have a times x minus 2 plus b times x plus 1 should equal to 1, which means if I let x equal to 2, then I get that 3b is equal to 1, so b is equal to 1/3. And if x is equal to negative 1, then I have negative 3a is equal to 1, so a is equal to negative 1/3. Well, then I can rewrite this as as negative 1/3 over x plus 1. But I'm going to write this as, of course, x plus 1 is 1 minus negative x. And I can write this as plus my b, which is 1/3, over x minus 2. Again, I'm going to write this as negative 2 minus or plus x. And in fact, I'm actually going to write this by moving my negative to the top, or you can think about it as multiplying by negative 1 over negative 1. Then I have, instead of a negative 2, that'll be positive 2 minus x, and a negative 1/3 on top. Well, I can write this as negative 1/3 times 1 over 1 minus negative x, minus 1/3 times 1/2 over 1 minus x over 2. If I multiply everything on this side by 1/2 over 1/2. Now continuing onward, that's negative 1/3 times 1 over 1 minus negative x, minus 1/6 times 1 over 1 minus x over 2. Which will get me negative 1/3 sum from n equals 0 to infinity of negative x to the n minus 1/6 sum from n equals 0 to infinity of x over 2 to the n. And there's possibly a little bit of simplification you could do, but for now, I think that'll do. Alrighty. So we've seen that we can go to and from functions in power series. And this is really just a small subset of all the functions you can represent as power series. We really just focused on ones you could represent using your geometric series representation, but there's really a whole lot of other representations that I don't think are studied in this course. But just so you know, they are out there. If you're interested, you can of course look it up on your own time because it's really quite fascinating. Alrighty. So let's actually go ahead and think about what else we can do with some power series. Because one of the things that is actually really useful is we can actually take derivatives and integrals. Derivatives and integrals. Because one of the main advantages of power series is it's really easy to take the derivative of a polynomial, but it's hard to take the derivative of some other functions. Similarly, it's super easy to take the derivative of an integral, especially when you compare it to some other functions. So let's say you have your basic geometric power series, the sum from n equals 0 to infinity of just x to the n. Well, if I took the derivative, all I'm going to do is I'm going to apply my power rule. So wherever I have an x, I look at the exponent, I multiply by that exponent, I decrease it by 1. There you have it. In fact, if we wanted to actually write this out, we could write out sum n equals 0 to infinity x to the n. This is 1 plus x squared plus x cubed, and so on. And if we took the derivative, well, that would be 0 plus 1 plus 2x plus 3x squared plus 4x cubed, and so on, which is, of course, equal to n times x to the n minus 1. If we let n be equal to, say, 3, well, then we'd have 3 times x squared. 3x to the 3 minus 1 is 2, 3x squared right there. Our first term would be 1 times x to the 0th, right there. Or technically, I guess our first term would be 0 times x to the negative 1, which is 0. 1 x to the 0, 2x to the 1, 3x squared, 4x cubed, and so on, which we would represent as the sum over all the n's of nx to the n minus 1. In fact, because our first term is 0, we'll often see it written as the sum from 1 to infinity of nx to the n minus 1. But regardless, we just apply that same power rule you've known since differential calc to our power series. Similarly, we could take the integral. If we have the sum from n equals 0 to infinity of x to the n, well, take the antiderivative. The power rule for that tells us we need to take the reciprocal of the exponent increased by 1, and then just increase the exponent by 1. And there you have it. So integrate that power series, we get same integral rules. So go ahead and take a look at this problem right here. Find a power series representation of natural log of 1 minus x. I'll give you a few minutes to work through that. And if you can figure that one out, think about maybe using some derivatives and integrals to help you out. And once you've done that, take a look at this one as well. And I'll give you a few minutes to work through that. All right, let's go ahead and go over these problems. So first off, we want to think about taking a derivative. We don't actually have this being in the form of a nice geometric series geometric series function. So let's think about the derivative. If you took a derivative, then we would have 1 over 1 minus x multiplied by the derivative of 1 minus x, which is negative 1. So negative 1 over 1 minus x. And remember, to do that, we took the derivative. Well, we can write this negative 1 over 1 minus x as negative this power series. And to undo this derivative taking that we did earlier, all we need to do is take the antiderivative. So undo it. The antiderivative is also known as the integral. Well, then that would become the integral instead from, the sum now from 1 over n plus 1 of x to the n plus 1. And here we're going to be summing this time from 0 to infinity still. And that would be our answer, because we took the derivative, converted it into a power series, and then undid our taking the derivative. For this next one, you could, of course, just multiply it out and find a power series representation that way. Alternatively, let's think about taking the integral. Well, if we take the integral of this, we can, of course, let u equal to 1 minus x. Then du is equal to negative dx. So it would become the integral of 1 over u squared du negative. And the integral of this is, of course, just 1 over u. Well, 1 over u would be equal to 1 over 1 minus x, which is equal to the sum from n equals 0 to infinity of x to the n. But then to undo this taking the integral, what we need to do is take the derivative. So when we take the derivative, we now have x times n, the n minus 1, sum from 1 to infinity. And there you have it. That would be our final answer. So we can take the derivative and the integral to find more functions that we can convert into power series. Now let's actually talk about kind of what exactly is going on when we create a power series. So one of the original ways to construct a power series was actually based on something you're very familiar with, which is linear approximations. So if we have a function, let's say it looks like this. We'll make it a little more curved. Let's say it looks like this. Well, at any given point, we can come up with a tangent line approximation. Suppose that this actually touches, so there we go. And we can come up with this tangent line approximation by taking the function value at this point and adding the derivative at this point and multiplying by our x value shifted to match that a. So when you think about it, if we plug in x is equal to a, well then this term would go to 0. We would just get f of a as our approximation. And when we have values close to a, well, we're basically just shifting over by the slope. So this is kind of how we create a tangent line approximation. We start with what you can consider our 0th derivative, along with an x of power 0, and then we add our first derivative, along with an x of power 1, but then we could, in theory, extend that. If we wanted a better approximation, what if we took the second derivative at that point, along with an x to the power 2. In this case, though, we're actually going to want to divide by 2. The idea is that for any given function, we want to make the derivative at some point a So this being the nth derivative to be equal to the nth derivative of our power series. So if we think of a function, we can start off with just the 0th derivative, f of a. And if we take the derivative of this, it's a constant, so it's going to go to 0. If we have our first derivative in our approximation as well, well, we take the derivative. This is a constant times the derivative of x minus a is just 1. So this would become our first derivative of this is f prime of a, so our first derivative would match. Our second derivative, we also need to match though. So basically I'm trying to say if I define my power series to be something like this, well, then when I take the nth derivative, what's going to happen is anything of a degree smaller than n is going to go to 0 because I'll take the derivative so many times that I'll eventually get down to a constant, take the derivative of the constant and get 0. When I plug in, when I have a value that's larger than n, or a term that's large that has degree larger than n, then I'll have some number of x minus a's left over. So when I plug in a, I'll have a minus a, and those will become zeros and also disappear. But when I have exactly my nth term right here, and I take the derivative n times, well, all of this, f to the n of a divided by n factorial, is all a constant. So I'm just taking the derivative of x minus a n times, which means I would have my constant part, and then I take the derivative of x minus a n times. So I would have n x minus a to the n minus 1 times 1, but then I take the derivative again, the n is a constant, so then I have n minus 1, which was my new exponent, and then I keep going, n minus 2, all the way down to n equals 1. And that's when I would stop for that term, because that means I had taken the derivative n times. But then all of this is, of course, just equal to n factorial. And then n factorial divided by n factorial is just 1. So this is actually equivalent. Which means if I make a series and I define it by taking the nth derivative at some point a times x minus a to the nth term divided by n factorial, I'm going to say that this series is going to match, if I have some other function, the derivatives at every, is going to match each derivative, the first derivative, the second derivative, the third derivative. All of those will perfectly match all the way to the infinitieth derivative at the point x equals a, which means that this power series would be a perfect approximation for f of x about a. And this is actually what we're going to call our power series representation of f of x about a. And this is actually one way we construct it, by using the nth derivative and simply following this construction. We're basically just extending this linear approximation to the rest of two higher order derivatives. Anyway, that's a bit of the intuition. I don't think it's necessarily covered in your course, but I think it's pretty neat, so I decided to go ahead and include it. Anyway, that's all I've got for you today. Thank you for watching, and have a great day.